Okay, here we're getting down to some beautiful stuff. This is Conceptuality12. Um, this will be this drawing will be a PDF file. Just want to go through it a little bit just to get you familiar with it. This is the universal dimensional click stops. This is the simplest bottom line way of imagining the construction of the self-organizing geometric entities, principles. Okay, so I've put everything in terms of the square root to just be consistent in the thinking of these dimensions as processes rather than as numbers. They're functions, okay, and they're exact and they're discrete and they're determined by the geometry. There's no measuring involved and there's no irrationality. It's completely rational and terminal, finished, and exact. Okay, so really we come down to this 1, 2, 3, 4, 5, 6 dimensions that determine everything that we've discussed so far in pure conceptuality. And I call this, presenting it this way, the universal dimensional click stops. Okay, now here's how you visualize it. All we have, as I mentioned in the writing, we have two triangles that are hinged right here like this. Okay, now all of the rest of universe is determined by the dihedral of this hinge. You know, that's all there is to the rest of the constructions, and I'll show you that. Okay. Wow, why is it stopping like that? Anyway, so let's put this here. All right. What we have is this turned this way, and so this dimension, as you would view it here, becomes 1/2 of the square root of 3, even though here it's 1, or the square root of 1. But visually it'll be shortened because you're looking at it from an angle, right? So here we have the angular relationship, and this is the first click stop is the star tet, or the tetrahelix. The next one is the duotet. The next one is the icosahedron, or the pentagonal decagon. The next one is the octahedron. The next one is the pentagonal decagon again. And then the last one, for our practical purposes here, is the tetrahedron. Now, the determiner of that angular relationship, obviously, is the vector across these points, which we've talked about before. Now, that vector is an exact length. For example, we know in the octahedron that it's exactly the square root of 2. Well, it has an exactness all along this arc, and that exactness is described by these mathematical operations are actually proportionalities or relationships. So this first one is the square root of 25/9, or 3/5. That if you have a 1 frequency triangle where this is equilateral triangle where this is 1, and you put this diagonal across here, that is this dimension, actually 5 divided by 3, or the square root of 25 divided by 9, you're going to create an angle that will give you the star tet. We'll start with the tetrahedron. We'll go here. We'll bring it over to the tetrahedron. This vector has to be 1, or the square root of 1. And so here we go through the series. This is the tetrahedron, right? And this is the value of 1, the same dimension as this, and we have the tetrahedron. So it takes two of those to determine, to create the whole tetrahedron, right? So that all we need is two of these little things here, and we end up with a tetrahedron, okay? So that's case number one. Case number two is the, well, let's just go in a different order. We'll say now in the case of the next rational, logical construction after the tetrahedron is the duotet, okay? So here it is. This is all you need to make a duotet is three of these, right? You could, if we didn't have this, we could just have a bend that is exactly that angle, and we have three of these, and we make a duotet. Okay, the dimension for this duotet is 2 times the square root of 6 over 3. That's this dimension if this dimension is 1, right? And the value is 1.632993162, but that's just a number. I mean, it's a discrete number, and it's as exact as you can be with mathematics. But when you have an actual duotet, you know that this dimension from here to here is exactly 2 times the square root of 6 over 3. I mean, it's an exact dimension. Okay, same as the argument that I've always made for the square root of 2 being the exact dimension internally for the octahedron. Speaking of which, here comes the octahedron. This is the square root of 2, and this is, it takes 4 of these, and you will have an octahedron, okay? Now, the next one is the pentagonal decagon, right, which we talked about before. And here it is. Let's see. It's this one here. Now, there's 2 cases here to be considered. There's this acute one, right, this, which is this angle through here, right? So that, if you have 5 of those, you have the pentagonal decagon. If you take the other case of it, which is here, all right, then you have, here's that pentagonal decagon that I just talked about right here. So if you had 5 of those, you would have a complete pentagonal decagon. Or you could have this one here, which is this in a different dimension, but it's still this exact piece. And in the case of this one, this dimension across these points is phi, which is 1 plus the square root of 5 over 2 is phi. Now, this is, in all rational ways of thinking, the most simplified and most primary example of the functionality of the dimension of phi. That's what it is, okay? So phi also, so in the case of phi, it would take 4 of these and 1 of these to make the pentagonal decagon, right? Okay, now we have the isosahedron, which comes into play here, and it's the same deal. It's the same dihedral angle for the triangles, and that is it would take 10 of these to fill out an isosahedron. But if you just had 10 of these and taped them all together edge to edge, it would automatically be a perfect isosahedron. So that's all you need to construct the universe is, in concept, these eternal dimensional integrities and the equilateral triangles that relate to them. You know, now that is true also for the tetrahelix. In the case of the tetrahelix, we have the tetrastar, and as we know in the tetrastar that we discovered that this dimension across here is 1.666666, 1 2/3, right? So if this is 1, then the diagonal across is 1 2/3. So it takes, let's see, 1, 2, 3. It takes 8 of these, and you will have the tetrastar, right? And it's exactly the same dimension here in the tetrahelix. If you had these and you just put them together edge to edge, you would come up with the tetrahelix. Just these externally create the whole conceptual structure of the tetrahelix. Now that's pretty neat. That we just have this ascending or descending order of geometric dimensional integrities, which I just simply call dimensions. They have the dimension of square root of 3 over 2. We have the dimension of 3 over or 5 over 3. We have we have the square root of 2, and so on. These this is 1 2/3. Those are dimensional integrities. All you need is this to build universe. Here's our octet star, and that is the octahedron. The octahedron fits right in here. So you can construct this just with these, right? So I don't see how it can get any simpler than that as far as describing how universe builds conceptually. The integrity of the thing is conceptually so simple that it's deceptive, that we try to make something complicated out of something so simple. So anyway, I hope that is what I wanted to say, and we'll see you next time.